So far we've been looking at problems with arguments for causation. We've talked about what is not sufficient to establish a causal claim. What we're going to do now is try to talk about what is sufficient. What would make a good argument for a causal claim? So suppose you have a correlation between two variables, A and B. We've seen that that's not sufficient to establish that A causes B, though it is relevant evidence. So a good question to ask here is, what more would you need to do to show that A causes B? What more do you need to establish to get a good argument for causation? Well, let me remind you what the possibilities are. If A and B are correlated, that might be because A causes B. It might be because B causes A. It might be that there's some common cause, X, that causes both A and B. It might be that there's a confounding factor X, something that causes one and is correlated with the other, or importantly, it might just be that the correlation is a coincidence. So what more do you need in order to establish that A causes B when you've got a correlation between A and B? What you need to do is eliminate these alternative hypotheses. You need to present evidence that 2 isn't true, that 3 isn't true, that 4 isn't true, and 5 isn't true. If you can eliminate all those alternatives, then assuming that those are the only possibilities, the only thing left is that A must cause B. So for a strong argument for causation, you need to eliminate the alternative explanations for why there's a correlation between A and B. How do you do that? Well, the strongest kind of evidence you can have for causation is the evidence you get from a controlled experiment. There's more detail about controlled experiments in the study guide, but the essential point to get is this. By design, a controlled experiment rules out all the alternative possibilities. In a controlled experiment, you make changes in one variable while keeping everything else the same. That's the tricky bit. And then you look to see if the other variable changes. If B changes when you changed A and everything else was the same, then that's very strong evidence that A caused B. Why is it very strong evidence? Well, because if you really did keep everything else the same so that only A changed, then that tends to rule out common cause explanations and confounding explanations, because all the possible common causes or confounding factors stayed the same. So they can't be responsible for B changing. Only A changed. That's the only thing that can really be responsible for B changing. Of course, the tricky thing is keeping all the other factors the same. That's why controlled experiments are difficult and sometimes expensive to do. And it's why it's very difficult to get the strongest possible kind of evidence for social policies, the effectiveness of social policies. For example, suppose you wanted to test the policy that introducing a tax on sugary drinks reduces obesity. That's a causal claim. The tax will reduce something, it will cause something to go down. To do a controlled experiment to determine whether that's an effective policy, you would need to have 2 cities or districts or states, and which were exactly the same as each other, except that in one you introduced the policy and in the other you didn't. And then you saw whether levels of obesity were reduced in the city where you implemented your policy, whether there was some difference between the 2 cities. But of course, that would be extremely difficult to get 2 cities that are exactly alike in all respects, except that you introduce the policy in one but not the other. Of course, it's in practice completely impossible to do that. although you can get a close approximation of a controlled experiment in that kind of case. So for practical or ethical reasons, it's sometimes just not really possible to do a controlled experiment. Here are some examples to illustrate that point. Let me just say something about claim number 3 here. The measles, mumps and rubella MMR vaccine causes autism. That, by the way, is completely untrue, a bit of fake news that was promulgated by various newspapers. No evidence whatsoever that it is true. I say that, but no controlled experiments have ever been done on this question, simply because it would be unethical to do that. It would be possible. You could take a representative sample of children, randomly assign them to one of 2 groups, give some of them the MMR vaccine, those in one group the MMR vaccine, and don't give it to the children in the other group, and then compare the rates of autism in the 2 groups over a long period of time. That would be a controlled experiment. But if there's even the slightest possibility that MMR causes autism or has any untoward effects, then it would be unethical to do an experiment like that. Or consider the global warming example. The majority of scientists now think that because of the increases in carbon dioxide and other greenhouse gases in the atmosphere, that's causing the planet to warm up. That's causing global average temperatures to increase. There's no controlled experiments at the planetary level which establish that. That would be impossible to do. You'd have to take 2 planets that were exactly the same, except that in one you artificially increased the concentration of greenhouse gases in the atmosphere, and in the other you didn't, and then you tested to see if one warmed more than the other. Practically impossible. So in these kind of cases, we can't really do controlled experiments for one reason or another. If we can't do a controlled experiment, though, we can still have very good evidence for or against these claims. For example, we have very good evidence that 4 is true, and very good evidence that 3 isn't true. Again, how do we do that? We do it by having evidence that rules out the alternative explanations. Although now the evidence is not going to be quite so strong as that provided by a controlled experiment, but it still might be sufficient to put it beyond reasonable doubt that the only plausible explanation of why our planet is warming, for example, is because of increased greenhouse gases in the atmosphere. So if you can't do a controlled experiment, but you do have a correlation between 2 variables, A and B, we know that the correlation by itself isn't sufficient to establish a causal link between A and B. What further evidence would help support the hypothesis that there's a causal link between A and B? Well, here are some further bits of evidence that can help establish causation when you can't do a controlled experiment. The correlation is strong and consistent. A happens before B in time. Higher doses are correlated with stronger responses, and there's a plausible mechanism linking A to B. All of these things would add some further support to the hypothesis that A causes B, and they would do that by, again, eliminating the alternative possible explanations, that there's a common cause linking A and B, or that it's B that causes A. So we'll look at an example now to explain these 5 additional criteria that can be used to establish causation. So there's a very well-known correlation between smoking and lung cancer, for example. Almost everyone in the world now accepts that that's because smoking causes lung cancer. However, there have been no controlled experiments on human beings to establish that causal connection. So how strong is the evidence? Okay, so there's a correlation between tobacco smoking and lung cancer. People who smoke are more likely to develop lung cancer than people who don't. But so what, says the tobacco industry. Correlation isn't sufficient for causation. That's not enough to prove that there's a causal connection between those two things. Maybe there's a genetic factor that predisposes people both to cigarette smoking and to lung cancer, for example. That's seriously an argument that the tobacco industry put forward in the early days of the debate about this question. So here's some of the additional evidence that we have that makes us 99% certain that cigarette smoking really does cause lung cancer. First of all, the correlation is very strong. You might remember I talked about how correlation can come in degrees of strength. If you have a very weak correlation, that's not very suggestive of a causal link. The stronger the connection, the more evidence you have that there's really something going on. And in the case of smoking and lung cancer, the correlation is very strong. You are a lot more likely, significantly, dramatically more likely to develop lung cancer and various other illnesses if you smoke than if you don't. Is the correlation consistent? What that means is it's found in lots of different groups of people. It can happen that although you find a correlation between A and B when you consider one group of people, for example, men or people under 35, the correlation disappears when you consider a wider class of people, men and women, or people over 35 as well as people under 35. But that doesn't happen in the case of the correlation between smoking and lung cancer. In that case, you find similarly strong correlations in men, in women, in all different age groups, in people in all sorts of different countries, and so on. That makes it very unlikely that the correlation is just due to chance. It's just spurious correlation found in one small sample, for example. Here's some charts just illustrating this kind of point, and it shows the correlation between cigarette smoking and death from lung cancer in lots of different age groups, men and women, and you can see that we've got a very strong correlation in all of those cases, in all of those different groups. The exact numbers don't matter, but you can see the general point, how the data points, the dots, are clinging very closely to this kind of straight line, meaning we've got a very strong correlation. It's not very noisy, a little bit noisy, but not very noisy. Okay, a strong and consistent correlation is making the evidence for a causal link between these two things a little bit stronger, but it doesn't really tell us much about what the direction of the link is. Maybe, for example, this is like the TV watching and depression example I used earlier. Maybe it's not that people who smoke tend to get lung cancer because they smoke. Maybe it's the other way around. People who have lung cancer for some reason tend to smoke more because they have lung cancer. So instead of A causes B, B causes A. How can we rule out that hypothesis? Well, in much the same way that it's ruled out in a controlled experiment. You look at what happens over time. In a controlled experiment, you vary A and then see if B changes later on. We can do the same thing here. We can, for example, look at rates of lung cancer against time, and compare them to rates of smoking against time. If we do that, here's what we find. So on this graph we have time along this axis going from 1900 to about 1980, and then up here we have the average number of cigarettes smoked per person per year. And you can see that starting in 1900 the rate of male smoking goes up and up and up and up and up, peaking around 1960s and then sort of levelling out. Correspondingly, we can see that the incidence of lung cancer in men starts to go up and up and up and up and up, almost in parallel, again, peaking now around the 1970s. The point is that there's a gap of about 30 years between these two things. So male smoking starts to go up, and then around 30 years later you start to see increases in the incidence of lung cancer in men. Similarly for women, we can see that women only seriously started smoking in the 1920s, and that's gone up and up and up and up and up and hasn't started to level off, although I'm pretty sure it has by now. And similarly, the gap of about 20-30 years, we start to see female rates of lung cancer also increasing. But the point is, because the lung cancer started to increase after smoking has increased, that tends to rule out or eliminate the hypothesis that it's the lung cancer causing people to smoke. These patterns are exactly what you would expect to see if, on the contrary, it was smoking that caused lung cancer. You would expect to, if smoking increased, then sometime later lung cancer would start to increase, and that's exactly what you find. We also find what is called dose response. So it's not just that if you smoke, you're more likely than people who don't smoke to get lung cancer. It's also true that the more you smoke, the more cigarettes you smoke, the more likely you are to get lung cancer. So, for example, if you smoke just 5 cigarettes a day, then you're more likely to get lung cancer than someone who doesn't smoke any cigarettes. A bit more likely. But it's also true that if you smoke 10 cigarettes a day, you're even more likely to get lung cancer than someone who doesn't smoke any cigarettes. And if you smoke 20 cigarettes or 30 or 40 cigarettes a day, you're even more likely than that to get lung cancer than someone who doesn't smoke. And if you smoke 100 cigarettes a day, you're almost certain to get lung cancer. So we have a dose response. The more of A you have, the more of B you get. Now that's exactly what you'd expect to happen if A caused B. In this case, this is exactly what you'd expect to happen if smoking causes lung cancer. But note that it rules out or tends to undermine certain common cause explanations. For example, if there was some gene that predisposed people both to cigarette smoking and lung cancer, then you wouldn't get the effect that the more cigarettes you smoke, the more likely you are to get lung cancer. That kind of dose response wouldn't be predicted by that kind of common cause explanation. So the fact that we do get this dose response, the more you smoke, the more likely you are to get lung cancer, that tends to undermine that kind of common cause explanation. Finally, we can ask this question: is there a plausible mechanism linking smoking to lung cancer? Can we explain at the sort of biological or cellular level how it could possibly be that smoking cigarettes causes lung cancer? And the answer here is yes, we certainly can describe plausible mechanisms that can explain why you'd expect smoking to cause lung cancer. As we know quite a lot about all the nasty things in cigarettes, such as tar, and how they affect cells in ways that make them more likely to become cancerous. And here we can do properly controlled experiments on animals. In those controlled experiments, what you do is you randomly assign groups of rats or mice to one of two groups, and then you, in effect, force one group to smoke, to inhale cigarette smoke, but not the other, and then you compare the rates of cancer of various kinds in the two groups. Since those animals are very, very similar, biologically speaking, in relevant respects to human beings, if we can see from such experiments that smoking causes lung cancer in them, it's pretty plausible that it's going to be causing lung cancer in human beings in much the same way. So all these considerations now are building up a very, very strong case that although we've got no controlled experiments on human beings that establish that smoking causes lung cancer, we do have evidence, which most people now think is fully sufficient to establish the claim that smoking causes lung cancer. Here I've just mentioned some of the evidence. I haven't even talked about all of the evidence that you could talk about in this context. So here are those 5 criteria again. The correlation is strong, the correlation is consistent, A comes before B in time, higher doses are correlated with stronger responses, and there's a plausible mechanism linking A to B. All of that, in addition to a correlation between A and B, provides quite strong evidence that A causes B. I mentioned before the case of climate change, global warming, where we can't do controlled experiments at the level of whole planets, although nonetheless the majority of scientists now agree that greenhouse gases in the atmosphere are causing the planet to warm. So you might want to think about how these 5 criteria apply to that case. We have a correlation between the increase in carbon dioxide, for example, in the atmosphere and increasing global temperatures. But how do we know that isn't just a spurious correlation or explained by some common cause or confounding, or perhaps it's the warming that causes the carbon dioxide to increase, so the causal link goes the other way? Well, I'll leave you to think about and do some research, if you want to, on how these 5 criteria apply to the case of global warming, and how these kind of considerations can be used to establish causal link between greenhouse gases in the atmosphere and global warming.